All right. Let's get started. Welcome, everyone, to the CHIP Landmark Ideas Series, Machine Learning and Revolutionizing Healthcare. Today, we'll be hearing from Mihaela the John Humphrey Plummer Professor of Machine Learning, AI, and Medicine at the University of Cambridge. The CHIP Landmark Ideas Series is hosted by the Computational Health Informatics Program, a multidisciplinary applied research and education program at Boston Children's Hospital, founded in 1994. You can learn more about us at www.chip.org. And this series features thought leaders across healthcare, informatics, IT, big science, innovation, and more. If you're interested in following along or participating in social media, here are some Twitter accounts that you can tag. We'll give a brief introduction to Professor Schaar, and then she will give her presentation. This is a webinar. You can put your questions into the Q&A. I'll also look in the chat for questions, but try to put them in the Q&A. And then we'll just wrap up after the Q&A session briefly. So Professor Schaar is a founder and director of the Cambridge Center for AI in Medicine. She was elected an IEEE Fellow in 2009. She's received numerous awards, including the Oon Prize on Preventative Medicine from the University of Cambridge, a National Science Foundation Career Award, 3 IBM Faculty Awards, the IBM Exploratory Stream Analytic Innovation Award, the Phillips Make a Difference Award, and several Best Paper Awards, including the IEEE Darlington Award. She's personally credited as an inventor of 35 USA patents, many of which are frequently cited and adopted in standards. And I will tell you that, and she's the most cited female AI researcher in the UK. And I will tell you that I've met with Dr. Schaar before and heard her about her work and what she's engaged in. And that's what makes me want to bring you to her today for what I'm sure will be a very exciting talk. She's very inspiring. She's very interconnected across a wide community of leaders in this space. And she's a mover and a shaker. And with that, let me unshare and turn it over to Dr. Schaar.
Thank you very much, Ken, for this opportunity, this wonderful opportunity to talk to your community. Let me make sure that indeed I can share correctly. Apologies. Just want to make sure that I can do this.
Looks good.
I don't know what's happening. Sorry, I apologize. It's 9 p.m. and I guess my brain is so at times tired.
It was looking good there for a second.
Even sharing a screen seems to be challenging. I apologize for this. I've done it a billion times before.
There it is.
Can you still see the slides well?
Yes, it's perfect.
Wonderful. So thank you very much, Ken, again, for the kind introduction. I'm going to talk today, I'm going to hopefully take you in a little journey of recent work in my lab aimed at empowering clinicians and medical researchers, as well as bioinformaticians, with some new set of tools and some new insights to distill new discoveries from data. I would like to start by introducing you to my fantastic lab members. They are highlighted in here, and also my postdoc and 2 research engineers that are joining us. Today, I'm going to really highlight the work of Jonathan, Christophe, and Georgie. I always like to start with this quote from Sir William Osler, who is the father of modern medicine. If it were not for the great variability between individuals, medicine might as well be a science, not an art. And indeed, our group aims at dealing with complexities of medicine, variabilities between individuals, which lead to different risks, variation in symptoms, health and disease trajectories, and responses to treatment. And the art of medicine has been to make judgments on the basis of this information to manage patients. And what our group tries to do is to use machine learning to turn this art into a science. But in order to be able to do so as machine learning researchers, since we are not clinicians and not even bioinformaticians, we need to engage with clinicians to have a conversation about the tools they need to develop and the insights they need to gather from data. So to understand these needs of clinicians, we have developed a set of online engagement sessions that we call Revolutionizing Healthcare. And we currently have more than 500 plus clinicians from all over the world involved with us in discussions about AI for healthcare. And the goal of these discussions is really to build a common language across these two disciplines and distill problems of interest to be solved by machine learners like me. If you are a clinician listening to this talk and you are interested in this area, please subscribe to it. If you are somebody in another field supporting the clinical community, please take a look at these Revolutionizing Healthcare sessions on our website, and you will see the various discussions we have, and hopefully you are going to get ideas about new problems you can solve. The opportunities that we envision of what machine learning can do in medicine are highlighted here. Delivering precision medicine at the patient level, understanding the basis and trajectories of health and disease, building all sorts of diverse tools to empower healthcare professionals, but also patients, inform and improve clinical pathways, inclusively utilizing resources more effectively, which is an important consideration in systems such as the NHS, transform population health and public health policies, and finally, enable new discoveries. And today I'm going to touch on 3 of these areas. I'm going to talk quite a lot about time series, understanding and discovery from time series data. I'm going to talk about how we can empower clinicians, but also researchers in the clinical domain with discoveries and insights. But before I'm going to do that, let me just, as I mentioned, my group is focused on building new machine learning methods to help clinicians and medical researchers. And the research spans different areas. We do quite a lot of work on machine learning to improve the quality and accessibility of data. So what do I mean by this green box here? We do work on data-centric machine learning, where we focus on building tools that improve the quality, the noise, and bias of the data, which play an important role in building high-quality analytics. Also, for many years now, we have worked on synthetic data, so building generative models with on the basis of real data sets, which contain and maintain the fidelity of this real data, but which have privacy guarantees. We built a variety of analytics. Today, I'm not going to talk too much about those, but a main focus in the lab has been individualized treatment effect inference, more recently causal deep learning, a variety of methods for time series forecasting, AutoML, and much more. But these analytics, in order to be helpful for the end users, which are clinicians and patients, they need to be interpretable. They need to be trustworthy and robust. And also, as I'm going to talk a little bit later, we need to enable new discoveries. And finally, to close the loop, we really are building quite a lot of new machine learning methods that enable us to build a new human-machine partnership. And for this, we are pushing the boundaries, going beyond inverse reinforcement learning, in trying really to understand not the black boxes of machine learning, but rather machine learning that is enabling us to quantitatively understand the gray cells of decision makers, in particular clinicians, with the overall goal not of replacing them, but rather augmenting their abilities. One thing that I'm going to talk about today is building this discovery ladder. You are probably familiar with the discovery ladder introduced by my former colleague at UCLA, Judea Pearl. But rather what I'm going to talk about today is a new discovery ladder, because I'm going to argue that in medicine, we need to go beyond Judea's discovery ladder. So I'm going to start in this talk by talking about associations. What type of features or features over time may be relevant for a particular, let's say, event of interest. Of course, we are quite familiar by now with causal relationships where there is maybe an underlying causal graph that is able to uncover the role of different types of interventions. For instance, is this specific chemotherapy drug for patients who have a low BMI and are women causing a liver dysfunction? But what I'm going to argue in this talk is that what we really need to go to is and discovering from data the governing equations of medicine. And for that, we mainly need to learn new dynamical systems. And this is something that I'm going to discuss, and I think is the most exciting part of my talk, but I'm going to take you in a journey, and hopefully all the different tools I'm going to present will be somewhat of interest to you. So I'm going to start by talking about identifying relevant associations over time. And for that, I'm going to take time series models that have been trained using machine learning and try to do machine learning interpretability of time series models, thereby going beyond machine learning interpretability of static predictions. Then I'm going to discuss how can we take expert equations that may be mechanistic models developed in a lab, either by a pharmacologist or by other scientists, and how can we complement that with real data? So how can we use these expert equations as inductive biases for deep learning and use deep learning to deal with model misspecification, thereby achieving more or less interpretability by design, but also bridging the gap between the lab and the clinic. And then I think the most exciting part will be how can we use data to really discover dynamical systems and discover complex equations from data. So let me start with the very beginning. And for this, I'm going to say, of course, machine learning has made great advances, but where it probably made the most important set of advances is on dealing with time series data. And if we have time series data models, whether it's statistical models or deep learning models, our own lab has built over the years a quite big amount of these models. You can take a look at one of our research pillars on our website to see some of the models that we have built. But whether you take a model developed by us or by other researchers, an important question is, what do these models learn and what do they learn over time? I'm going to tell you about that, but before I'm going to do that, let me tell you that we are going to have, actually not end of October, I apologize for this mistake, we are going to have tomorrow, December the 4th at 4 p.m. UK time, a session where we are going to describe some of cutting-edge machine learning methods that we have developed recently, going beyond neural ODEs for time series models. So if you are interested in time series models at the cutting edge, please join us tomorrow in another engagement sessions, this time not dedicated to clinicians, but rather to analytical people like you who may be interested in developing models for healthcare. What I'm going to talk today, though, is how can we take these machine learning models that have been trained for time series and come up with post hoc explanations, thereby discovering associations over time that may be of interest. And for that, we need to go beyond interpretability of static predictions. We have a large number of methods that are working for interpretability of post hoc machine learning models for static prediction. But what about time series? And for that, I'm going to introduce you to a model that we call DynaMask, which was published last year in ICML 2021. But I want to also tell you about, just briefly, I'm not going to go into the details, but I want to bring to your attention the fact that while we have many methods for interpretability of static predictions, we lack research in interpretability of black box model for other purposes that are important in medicine. For instance, time series phenotyping is something that we do a lot, and learning clusters of patients that may evolve differently and differently over time is an important unsupervised learning problem. Yet understanding why certain patients are clustered together by these black box models is not often understood. So again, recently we built machine learning interpretability for such unsupervised learning models, label-free explainability. And this is, as far as we know, the first method that is able to do both feature and example-based explanations of unsupervised learning methods. Also, more recently, we have the first machine learning interpretability for treatment effect estimation methods, for heterogeneous treatment effect estimation methods. So trying to understand what these different machine learning based methods for heterogeneous estimation of treatment effects do really learn. And this is a paper called Playfully Interpretability. But as I mentioned, I'm going to focus on time series. So the questions that we ask ourselves is, do standard interpretability methods work when we want to interpret time series forecasting? And the answer is no. There is this wonderful paper of NeoRIPS 2020 by Mihaela and his co-authors, where they are showing actually that current methods, whether it's LIME, SHAP, learning to explain, integrated gradients, are not able to uncover the true saliency map that may be really what drives the machine learning models. And you see that in here. You see the true saliency map for a TOE example, where we do know the underlying saliency map. And you see that the existing machine learning interpretability methods that are designed for static interpretability are unable to uncover that. So why is really that? Because the time context matters. Of course, when we do time series prediction, we know that all these machine learning methods are taking the time series into consideration. So the same thing is needed for interpretability. And the time dependency is ignored by these interpretability methods. So this is why in this work that we call DynaMask, we have built this dynamic perturbation operator where we perturb each particular time series point using neighboring time, as shown in here. And then we are estimating the impact of the perturbed input. And we do that as a linear combination of the different past inputs. So in this way, the time dependency is integrated in the perturbation. And in DynaMask, we are using this idea. So we aim to interpret the predictions made by a black box model, as shown in here, for a time variant series X, which is this black box model F. And the objective is really to give a saliency score for each component of X. And in DynaMask, the saliency scores are stored in this mask M of the same shape of the input. And to detect the saliency information in the input, the mask will produce this perturbed operator, perturbed version of the input, which we are feeding to the black box model. And this results in a perturbed prediction, which we are then comparing with the original prediction. And this error is backpropagated to obtain the saliency map contained in the mask. Now, this is all very easy. The question is, though, how can we come up with masks that are parsimonious And by parsimony here is we want to capture only the minimum amount of features that have led to this prediction. So for instance, if all the features are important, green is important, like in the upper part of the image, you see that almost everything is important. Something like that will not be useful as an explanation. What we would need is the most parsimonious explanation. So the minimum number of features that have led to this prediction. So to enable and enforce parsimony, we provide this type of regularization of DynaMask to enforce sparsity. Another thing that we want to do is we want to have congruous explanations. And what we mean by that is we want to avoid quick time variation of the saliency map, as you have seen in the example before. So in order to enforce these saliency regions to connect in time, we will really like to penalize jumps of the saliency maps over time. So we do not want something in the, like in the picture above, but more something like in the picture below. So DynaMask adds a regularization to penalize such saliency maps over time. Now, with these two concepts together, DynaMask is enabling us to build a legible interpretability method. And we would like to make this notion of legibility quantitative. And how to do that? For that, we are going to use information theory. I'm going to skip all the details of how we build it and the proofs associated with it, which you can find in the paper. But I'm going to playfully highlight to you the idea with this particular depiction here. What you see here is that we are using the mask information and the mask entropy as two measures of this legibility. So what we see here is that if it is to deal with parsimony, we would like to have the minimum amount of information encapsulated into it. And if we want to have congruity, we would like to have the minimum entropy. So ideally, we would like something like in the left bottom corner. Low information and low entropy, so minimum number of information that has led to this particular prediction. And indeed, you can see that DynaMask is able to achieve this legibility. You see again the true saliency map for this toy example. You see DynaMask with the entropy associated with it. And you can see all the static methods associated with it. And you can see indeed the DynaMask is the one that is not only closer in terms of how it looks like as opposed to the true saliency, but also the legibility of it is high. This is a toy example. In the paper, we have a variety of examples, inclusively from the wonderful MIMIC dataset. And you can see how this DynaMask can be used to identify what features were important and what features were important over time, as identified by a particular black box model that this DynaMask was applied to. I do not think the DynaMask is the end of the story. I think it's the beginning of the journey, but it highlights the need for at least our machine learning community to engage with this type of tools and build new tools for machine learning interpretability, not only for the static setting, but also for time series setting, and as I mentioned before, treatment effect estimation or unsupervised models. Now, let me move to something, and if you want to engage with the work that we have done over the years on machine learning interpretability, here are our papers, and here is the GitHub of the lab with papers from a variety of students over the years engaged with this agenda. Let me now move to the next topic. And here I'm going to really assume that we have in this time series setting an expert equation that may come from the lab, for instance, from pharmacology. And we would like to apply it to a patient in the clinic. How to do that? How to bridge the lab and the clinic? So the way in which, the reason that this was so important is in COVID, but this is more generally true, we would like to identify what type of treatment to give to a patient and what dose we may want to give them. This is the field of personalized therapeutics where machine learning is starting to make increasingly more progress. Again, in our lab, we have a large large number of papers in the area of machine learning for estimating heterogeneous treatment effects or individualized treatment effects. But the challenge we often have is that we have very limited data. And, oh, sorry, for just one second, I want you to highlight, if you are not familiar with this area, I'd recommend reading a tutorial paper that we wrote a few years back together with my former brilliant students, Ivana and Ahmed, where we highlighted the opportunities and in this area. And one of the opportunities that we highlighted when we wrote this paper is the ability to take already mechanistic models that may be introduced for pharmacology and use them to improve predictions made by machine learning. This idea, which appeared at the end of 2019 and was just mentioned in that paper, came to much use in COVID-19. Because what we had to deal with is we wanted really to empower clinicians at the University of Amsterdam Medical Center, which had relatively few patients, only a few hundred, then a few thousand only. And yet they wanted to learn how to give dexamethasone to patients in their ICU wards. So for that, we built this paper in collaboration with them. So Zhao, my PhD student, together with two clinicians, Lucas and Paul, we have used ideas from pharmacology and embed them into machine learning to improve their performance. Let me tell you about that. So I'm going to start with a clinical problem. The focus was the use of dexamethasone for COVID-19 patients in the ICU was a complex one because managing the level of immune response of patients in the ICU is essential and yet challenging because the right level of this immune response varies across the different patients. For most patients, we would like to reduce the immune response to avoid a cytokine storm, for instance, and consequent organ failure. But for patients that may have some other type of secondary infection, for instance, a bacterial infection, we would like to keep their immune response activated. So knowing how to act was challenging. We do have from pharmacology very powerful models for dexamethasone. However, a challenge associated with these PKPD models, which were developed by pharmacologists, is that they were developed in the lab. Yet in the clinic, we do not have often access to this type of biomarkers. So you see here this pharmacological model, this PKPD model, that has all sorts of information that is accessible in the laboratory setting, a set of expert variables that are available in the lab, but they are not, unfortunately, available to the clinician. What is available to the clinician is often something like a C-reactive protein. So how can we really bridge this gap between the lab and the clinic to empower clinicians to decide whether to give dexamethasone and in what dose? How to do that when we have only relatively few patients, initially just a few hundreds. So for that, we really build this idea that you can take a mechanistic model, and this idea is quite general. You can take any mechanistic model, but in this case, we took a pharmacological model. And often pharmacological models describe the dynamics as shown in here of carefully chosen medically meaningful variables in terms of an ordinal differential equation. But however, these models only described, as I mentioned, a limited collection of expert variables. And I'm going to call these physiological variables. And often these variables are not available in clinical environments. Then, on the other hand, we have clinical biomarkers and endpoints that are measured frequently in the clinic. But And they are important for decision making, but they are not modeled by PKPD due to their high complexity. So what we would like to do is we would like to use the pharmacological models in clinical environments. And for that, we will need to build a link between the lab and the clinic. And the way we are going to do that is using machine learning. So what we did in this NeoRIPS 2021 paper that Zhao developed was this method that we call latent hybridization model. And this is a very powerful idea where we take a mechanistic model, an ordinary differential equation, for instance, that relates the expert variable with each other, as well as their evolution over time. So it's a dynamical system here that's used. And we embed it into a machine learning model, a system of neural ODEs. And through this hybridization approach, pharmacology joined forces with machine learning to capitalize on the strengths of both of them. Note that in this latent hybridization model, we use observational data to learn both the evolution of the unobserved latent variables, as well as the relationship between the measurements and all the latent variables. And the expert variables from the pharmacological model and the latent variables in the larger model. Now, we show in this work a variety of very important extensions. For instance, we can include static covariates, which are the features of the patient, thereby enabling personalization, as well as we can deal with informative sampling, which is important because the data is irregularly and informatively sampled. Finally, we assume that in many settings, people are assuming that the mechanistic model, in this case, the pharmacological model, is correct. We do not assume that, because the reality is that the model may be wrong in several ways. The obvious way in which this functional form may be misspecified is that maybe the pharmacologist may assume a linear model, while in truth, we actually have a nonlinear model. And many existing techniques can address this misspecification and could be integrated into this latent hybridization model. Alternatively, it may be that the system of expert variables is maybe not self-contained and their evolution actually depends on additional latent variables. And these are things that potentially may not be observed. And in this latent hybridization model, through this hybridization, we are able to deal with such model misspecification. Now, how do we really learn? We learn as shown in here. So we train and do prediction via this Bayesian variational inference approach, where the encoder network, as shown in here, is inferring the latent variables and the physiological variables. And the decoder is a standard numerical ordinal differential equation solver. And we do end-to-end training through a joint sensitivity gradient. Let me just say that given the training data set, we use this amortized variational inference approach. And what I'd like to say is that the training procedure is kind of agnostic to the exact choice of the variational distribution and the encoder architecture. And you can use other architectures as well to enable this type of hybridization. So there is a lot of flexibility in this process. Now that we are able to do that, we can use the clinical measurements in the ICU of C-reactive protein and infer from the C-reactive protein the expert variables, which are in this case the immune response and the dexamethasone concentration. And the reason this is again important is that if we can infer these expert variables for the immune response to viral infection and dexamethasone concentration, we can help clinicians understand their patients and understand how the pharmacological models on the basis of this inferred variable, expert variables, are going to evolve. And this can provide them with information that they can use in their decision-making. So we take the information that we have in the clinic and understand the expert underlying variables, thereby being able to provide them to the clinician who now can use these pharmacological models to understand the evolution of this particular patient over time. But there's one more thing that we can do with this. Because we have relatively limited data, initially we had 100 patients, then 200 patients, then 500 patients, then only 1,000 patients. The conventional machine learning models were not able to do high quality prediction in the future. So what you see here is the root mean square error, so hence the lower the better, for predictions made over time of disease progression and response to treatment. And what you see is that this latent hybridization model performed the best, and it kept performing the best because we have relatively few number of patients. So pure data-driven approaches, machine learning approaches, from conventional neural ODs to all sorts of deep learning methods, LSTM methods, and beyond, were not able to learn very effectively from data. So by injecting this inductive bias and these priors from pharmacology, we were able to learn much faster. So here is where knowledge from pharmacology, and possibly in your case, knowledge from another area about mechanistic models, can be embedded to improve the performance of machine learning models in settings where we have very few data points. So often there is this belief in our machine learning community that the more data, the better. And what we show here is that if you have such inductive biases coming, from instance, from pharmacology, you can significantly outperform conventional, even state-of-the-art machine learning models. Also, this does better than purely expert-driven models that we have used and compared with in our paper. What's maybe most interesting, if you are coming from the clinical domain, this paper, while appearing in a machine learning conference, was also developed with clinicians. So we have a very extensive discussion of the use that these clinicians have made of this model while treating patients during the pandemic. Let me now move to the final part, and I think the most exciting part of this talk. How can we discover equations from data? And first, I want to tell you about what do I have in mind when I say discovering equation, discovering models. We really would like to have models first, because we would like to have some powerful conceptual representation which enables humans to understand the variables that play a role, their relationships, in order to be able to understand, but also experiment and act. In the first example I showed you today, it was a completely associative model where post hoc we learn variables and variables important and how they evolve over time, as learned by these black box models. In the second scenario, I was showing to you how we can take something that was understood by experts, in this case pharmacologists, and how we can embed it into deep learning and take it to data, correct for model misspecification. Here I'm going to directly say, let's forget about the deep learning models. Can we directly learn using machine learning these powerful mechanistic models from data? So for that, we need to go beyond feature and example-based interpretability, and even beyond standard causality. So what do I have in mind when I say governing equation is a mathematical model that describes how the values of an unknown variable change when one or more of the known variables change. And I'm interested in compact and closed form equations. And here I want to give you an example as what I have in mind. And the examples I'm going to give you are initially from physics. We all have seen through our high school or undergraduate studies these examples from physics, where we learn governing equations in the form of explicit functions, implicit functions, ordinal differential equations, or partial differential equations. And we all know this example from relativity or Newton's law or heat equations. The question is, why do we want that? Because such examples are concise, generalizable, amenable to further analysis. We can really understand stability very easily if we have this type of equations. And they are transparent by design and easy for humans to engage with. And you may wonder at this stage whether such governing equations exist in medicine. And the answer is yes, they do exist in risk prediction, where we, for instance, statisticians may have learned the estimated baseline cumulative hazard, for instance, for breast cancer, like in this case at the NHS PREDICT model. And they exist in pharmacology, they exist in disease progression, for instance, tumor growth, and I'm going to go to this example. And we are all somewhat familiar, unfortunately, with SIR and SCIR models from epidemiology, where in COVID, the spread of infection was modeled. And these equations are often discovered by scientists, whether it's pharmacology or epidemiology or statistics. They are often discovered by human experts. So from the physics to the physiological to the psychological, we have human experts looking at data and discovering these equations. And for that, they need domain knowledge, intuition, experience, brilliance. And I'm going to argue that we need experts, but we need to empower them with additional tools. Because the reality is that this expert-driven discovery, it's not perfect for medicine. Let's think about it. Very often the hypotheses that humans have put forward over the millennia may not be correct. We as humanity believed for a very long time that the world is flat. Also, often humans cannot keep in their head complex data and complex data evolving over time. So they may ignore different types of data to support maybe a wrong hypothesis. Also, at other times, a lot of variables are discarded because of that. And as I mentioned in the example before, at times things are very controlled and simplistic in the lab, but not in the real world. And yet we collect data very often in the real world, and we want to build models that deal with the complexities of the real world. So we'll argue that machine learning can help in this journey. I'm going to start with a very simple example, but then I'm going to move to the other one, which I think it's even more pertinent, learning ordinary differential equations. But let me start with risk equations very briefly. As I mentioned before, we have these NHS PREDICT equations. And a few years back, together with my former student, Ahmed Allah, who is now professor himself in Berkeley and was for some time in MIT Harvard ecosystem, we wondered about this idea, can we take a black box model and turn it into a white box model, an explicit function? And for that, we built these symbolic meta models that take this black box model and turn them into a white box explicit function. So the focus here would be to take a black box model, for instance, a deep learning model, and try to find for it, with symbolic meta models, an approximation that is in the form of an explicit function. I'm not going, in view of time, to go into the details of this, but let me say that in order to be able to do so, a very key part of the puzzle is to learn good representation and good basis. In the work with Ahmed, which is the original work, we used MyRG functions to do that. In later work with Jonathan and Yao, we started to look at a symbolic pursuit approach and a matching pursuit approach, where we are learning basis and improve the basis depending on the error resulting from the approximation. I'm going to show you this work that we have done together with Ahmed and a few clinical collaborators to show to you what's possible in the simpler setting before I move to the ordinal differential equation, the time series setting. So in this work together with Ahmed and our clinical collaborators, we showed that we are able to do better than NHS PREDICT, which is the clinical risk score for breast cancer prediction for survival. And it is used both in the UK and United States. And we were able to show that this machine learning, automated machine learning model that we built a few years earlier, autoprognosis, is indeed able to do better than NHS predict. And in this paper that appeared last year in Nature Machine Intelligence, we validated this in a very large study, both within the data set in the UK. So the model was trained in the UK, validated in the UK on a holdout data set, and also validated in the United States without seeing any of that data. We were able to show that autoprognosis significantly outperforms the regression-based method that NHS Predict is based on, but just performance improvement is not enough, because in this area we need a transparent equation. So for instance, the Joint Committee on Cancer would mandate a real equation. So we use this symbolic meta model approach to learn equations. I'm not displaying them here, they can be found in the paper. But what I want to say that if we are able to learn these explicit equations in the form of meta models, we can then use them to make predictions instead of the black box autoprognosis model. So we can use autoprognosis to guide us to find this meta model, but as soon as we found this transparent equation, which has the same transparency as, it's still an explicit function like a regression, but unlike regression, doesn't have only linear terms. It also has nonlinear terms and nonlinear interactions, which are important for predicting accurately both the population of women as a whole, as well as subpopulations. So this is a very important component, if you like, learning this explicit risk formula in providing transparency. So in this way, there are really no advantages to use regressions. You can use a black box model, and through symbolic meta models, provide this explicit risk formula. This is good in the case of static risk predictions. But what about dynamical systems? Because as I mentioned, it is dynamical systems that we would like to understand. This is really the highest level on the discovery ladder. And in medicine, dynamical systems are described by such ordinary differential equations. And this is a much, much harder problem. So what is the problem that we have? We have a data set that's collected somewhere, for instance, in the clinic. And on the basis of this, we would like to discover the underlying differential equations. Let us see how this was solved before. The way in which has been solved before is through variations on symbolic regression. So symbolic regression itself cannot solve this problem, but variations on it, such as two-step sparse regression, two-step symbolic regression, are able to do that. However, they have an important disadvantage. They require us to estimate the derivative from noisy data, noisy real data. This is a very hard problem, and most of the time is not done very effectively. At this stage, if you are a machine learner, you may have heard about neural ODs, so you are going to say, what about neural ODs solving this problem? Let us note that neural ODs are wonderful for prediction, but they are not providing closed form solutions. So they are not up to the task at hand. They are not able to discover equations. Also, they are not suitable for chaotic systems where a small variation in the initial condition will lead to a big deviation in the later part of the trajectory. And you are going to see a little bit later that actually neural ODs have a lot of problems when you deal with real data and real, more powerful clinical data. But let me say that if you are interested in this approach, you are not interested in understanding, but just learning about predictions of time, then we do not need necessarily closed form equations and can do neural ODs. Or, as I mentioned before, we have recent advances that improve significantly on top of neural ODs, such as, for instance, this relatively recent paper that we call NeoLaPlace, that is capable to learn much more effectively from data than neural OD. But for the purpose of this talk, we want to really learn and discover equations. So for that, we created this system, this idea, this method that we call Decode, together with Zhaoxi and Christophe, which is discovering closed form ODs. And the key insight behind Decode is the variational formulation of ODEs, which is going to enable us to establish a direct link between the trajectory x of t and the ODE f, while bypassing the unobservable time derivative x of t. So just very briefly, we need to familiarize ourselves to see this magic. And if you are not in the machine learning community, just bear with me for a little bit to unravel this magic. What's the magic here? We can use this variational formulation of ODEs to characterize an ODE without referring to the derivative. And this is achieved by introducing some type of functional that takes the original function f, the trajectory x, and a so-called testing function g. And it is this testing function g which we can now design. And it is their derivative of g, that we need to use, and no longer the derivative of f. So it is really important to know that this expression no longer contains the derivative of x, but rather the derivative of g. And because we can design g, we can easily compute that. So this variational formulation states that this differential equation holds if and only if the corresponding functions are equal to 0. And this may sound like a useless theorem, but it is not a useless theorem for us because it is constructional. The way in which this is becoming constructional is that it is going to tell us that indeed minimizing the value of this functional through an algorithm is going to correspond to finding better approximations of the true ODE. A theorem that we proved on top of this variational formulation is telling us that minimizing the objective should correspond to finding these better approximations to the true ODE. And in addition, is constructional because it tells us something about how to select G. In particular, a Fourier sign basis is a good choice. With this in mind, now we can describe our algorithm that has two steps. In the first step, we are actually taking the data set of these observed trajectories and we denoise them and interpolate them to get these estimated trajectories. Now, we estimate the trajectories and not the derivatives, like in symbolic regression. So with this in mind, now we are solving this optimization, which consists of the functional that we defined earlier. And we evaluated on all the estimated trajectories from the first step and all the pre-specified testing functions. And the actual optimization now can be done by any algorithm that is suitable for symbolic regression. Now, we took this to first to discover some equations that we know. So what do I have in mind here? We took data, we add all sorts of perturbation to it, all sorts of noise, and we try to see, can we recover still the dynamical systems that have generated this data as a proof of concept? And for that, we considered a few dynamical systems and compared it with two-step symbolic regression. First, we looked at Gompertz models and generalized logistic models, which are asymmetric growth with saturation. So the reason we chose these models is often in medicine, we have asymmetric growth with some saturation. And we use this to see if we can learn from data with different levels of noise, different sampling rates, different number of samples, whether we can unravel the true equations. And you can see that indeed decode outperforms the benchmarks under all the settings, but especially the more challenging settings where we have large noise, few observations, and few irregular observations. What about chaotic systems? Because again, very often we may have chaotic and non-periodic systems. And for that, we try to learn to see if we, from data we can unravel, we can rediscover the chaotic Lorentz system. And what you see is that not only that decode does better than symbolic regression, what's interesting is it does better, but it even does better in terms of prediction than neural ODs. So as I mentioned, neural ODs cannot even learn equations, but they cannot even predict from such a data. And the reason behind that is, again, neural ODs are solving the inverse value problem. And in settings in which we have chaotic systems like these ones, they are incapable to make predictions. And yet decode is able to discover an equation and make correct predictions over time. What about discovering something we don't know? So we took for that a discovery of temporal effects of chemotherapy from data. And the temporal effects on chemotherapy on the tumor volume can be shown in this example in here. And you can see that initially it decreases in response to treatment and then grows again due to drug resistance. And multiple models exist for unintervened tumor growth, but only few models exist that can capture the effect of chemotherapy on the possibility of relapse. So what we did is we used 8 clinical data sets on cancer patients that measure the tumor volume over a year in patients undergoing chemotherapy. And we wanted to see if decode and symbolic regression are able to capture these trends. And what you can see here is that decode is learning a more compact equation as opposed to symbolic regression. And also, unlike symbolic regression, is able to capture this trend of decrease and then relapse of the tumor volume. Is this really the underlying equation of how these tumors evolve over time? For that, we will need to engage with researchers and go to the lab. But this provides a way to learn from complex, messy data, these mechanistic models. Can we go even further? The answer is yes. We can also learn not only things like ordinal differential equations from data, but we can also learn partial differential equations. And this is even more complex and requires really building even some new math. And for that, together with Christophe, we build this framework, as well as the mathematics required to learn partial differential equations from data, and we call this Decipher. This brings me to the very end of my talk. I took you hopefully on this journey of where we are trying to go with machine learning to provide discovery and insights. At the lowest level is learning associations and also learning features and feature importance, especially in the time series settings or when we are interested in interventions. This will provide a first hypothesis and insight that clinicians can use. Then, of course, we can have causal discovery and causal graphs. And finally, I'm arguing that in medicine, what we really need is to learn dynamical systems and learn these governing equations of these dynamical systems that the human bodies really are. With this in mind, a talk to such want to say that I'm recruiting not only PhD students and postdocs, but also collaborators, hopefully, that would be interested to join forces with us to take some of these machine learning tools to real problems, real data, and real interesting problems in medicine. Thank you very much for the opportunity to really give this talk.
Well, that was a really scholarly, in-depth look at the opportunities and the achievements of applying machine learning to medicine. And you gave some really terrific examples. Let me drill down a little on one of them that you referenced, just to get an idea at a high level for the sort of mixed audience of experience that we have on the Zoom today. You mentioned the SIR models for example, COVID. So in a predictive task, incorporating the SIR models, these models that tell us how quickly COVID might spread depending on how many people are susceptible and how many people are infected at any given time. Jumping off of the type of example you gave for dexamethasone with PK/PD models, but now thinking about this traditional epidemiological modeling married to machine learning, what kind of task would be most benefited from that, the merging of those two?
I want to thank you for that question, because during COVID, again, together with Zhao Zhiqian and Ahmed Allah, we built a system, we built a model exactly to do that. So we took an epidemiological PCR model, which was really developed, of course, by epidemiologists. And what we did is we embedded that into a deep learning model that is sandwiching this epidemiological model. And it allows, on one hand, at the lower level, similar to the latent hybridization model that I presented here, it enables us to correct model misspecification by putting a deep learning model that is correcting this epidemiological model. But what was interesting in the paper, we also have an upper layer model that enables us to learn across the different countries. So it will allow us to do some type of transfer learning where we are learning from one particular data given their unique features to identify the R0 to be put in the SCR model in another country, to be able to make this type of predictions even in the early stages of the pandemic where we may not have had enough.
Thank you. And so what kind of inputs were the control measures in the different countries part of the inputs for those?
Exactly. So we benefited from this huge data set that became available quite early in the pandemic, where we knew not only about the number of people infected and deceased, the number of people deceased, but also we knew all sorts of information about the country measures, for instance, school closures, airports being closed, all sorts of non-pharmaceutical interventions that the different countries were taking. And the goal was to build a predictive model where, on the basis of what we have learned in one country, we could transfer predictions about what happens in another country, and try to do that within a predictive framework rather than a causative framework, but trying to really extrapolate across these different countries to really learn from each other and be able to identify what would be the resulting impact. So the reason I like this question very much, thank you for it again, is showing this kind of new paradigm we are trying to push, which is, let us not go directly to data with just deep learning. Let us try to use mechanistic models that exist in these powerful fields, epidemiology, pharmacology, biostatistics, and use them in conjunction with machine learning models to take them to data, especially data sets that may be of smaller size, which is unfortunately often the case in the beginning of a pandemic or in the clinical setting where we may not have a large number of patients, thereby pushing the boundaries, if you like, of machine learning in these lower sample regime settings.
That's great. Thank you. Let me go to a question from Tim Miller, one of our faculty, and he asks, who decides whether a model is interpretable enough to use? Does every practitioner need to understand the model, or just the people responsible for the model deployment? Some of these models are more understandable than, say, a matrix of neural network weights, but real understanding is not trivial and requires an unusual combination of medical and mathematical training.
Thank you so much for this question. So first, I'd like to say that, again, I want to refer you to these engagement sessions we have with clinicians, these revolutionizing healthcare sessions. We had almost 20 of them by now. And one of them focused on exactly this question. So we had a large number of clinicians thinking with us about the types of interpretations we need. And we came up with at least 4 different types. And I actually summarized that discussion in a blog that you can read on our website. But to summarize is, in some settings, example-based explanations would be enough, meaning what examples are most pertinent to this particular prediction. In another case, we discovered that clinicians may want features and look at features to do the debugging. And I agree with you completely that in all these settings, we need clinical understanding as well as understanding of what data was fed through these models to train them, and really what comes after it. But in other settings, for instance, again, many people are familiar with regressions and are familiar with explicit functions. So many clinical bodies, the Joint Committee of Cancer, some of the NICE regulation in the United Kingdom requires an explicit function. So they really would like to have an equation in the form of an explicit function, not necessarily linear like a regression, it could be nonlinear, but an explicit function. So this is why in this work with Ahmed and then later together with Jonathan and Yao, we looked at learning explicit functions using black box models. Then if you look at the very, let's say, final stage of this presentation today, I showed you this mechanistic model. So pharmacologists, for instance, and many scientists are very familiar with these ordinal differential equations. And what we want to do in this last part of the talk is to learn such mechanistic models, such ordinal differential equations and partial differential equations from data. So thereby empowering pharmacologists and scientists with these new tools. But what is useful for different communities is really quite different. So this is why we built a large number of tools to enable the community to engage and debug models with the overall goal of indeed identifying, do these models learn the right thing? Do they learn the right thing for these patients? Are these the right variables to be looking at? Do they evolve over time in the way in which we expect? You are alluding to where we are going, which is not model interpretability, full stop. Model interpretability for the role of getting experts, clinicians, and scientists to engage with these model explanations and debug the model based on their knowledge.
So
then I can stay and take many more questions if necessary. I'm awake now.
yeah.
I was afraid
this timing is perfect. This is great, and it's very nice of you to stay up late to join most of us.
I'm awake
here in the state. So here, I think, but this is around the time we'll generally wrap up our sessions, and so let me connect what you were just talking about to the final question from Don Goldman, who's a professor and infectious disease expert here at Boston Children's. Do we want to substitute data science for the art of medicine? And can you talk about that tension?
So I often talk about terms of a metaphor. I often say I would not like to go into a plane that it's an automatic pilot, and I would not like to get into a plane that has where pilot has no instruments at all. As a patient, I would like to move into a plane of healthcare where there is a pilot, in this case, a clinician, but is empowered with tools to analyze the complex information about me, my information over time, potentially my genetic information, as well as my family history, and possibly much more information from my wearables, to use this information together with tools from machine learning, to distill insights that may be pertinent, that are validated thoroughly, to help him come up with recommendations and explanations for me. So I would say the tension is, right now, we believe that in our human brains, clinicians can do everything. And the reality is that clinicians can do a lot, but they can be further empowered by data, and insights gathered from this data are difficult to do without machine learning, especially when we deal with complex genomics data, time series data, and diverse sources of information, I would say.
Nice. Well, Professor van der Schaar, that was a fantastic talk, and I encourage folks on the Zoom to take you up on your offer to collaborate. I know that you're a highly collaborative researcher and very successful at collaborations. So it's a generous and wonderful offer, and I really do encourage the participants today to take you up on it. Let me
Thank you for the
again,
opportunity.
and we will be in touch with you as well. And I'm going to just briefly give us a quick view of upcoming talks as well. Nate Cooperman, emergency physician, focused on global level collaborative research networks. Wanda Barfield, a director of reproductive health at the Centers for Disease Control and Prevention, who will talk to us about up-to-the-minute issues around maternal health. Sebastian Schneeweiss, a pharmacoepidemiologist, who will talk to us about the advantages and pitfalls of using real-world data. Ray Kurzweil, inventor and futurist. Christina Farr, former CNBC technology and health reporter, now a venture capitalist. Rich Miner, inventor of Android. Alan Brandt, a professor of the history of medicine and an incredibly inspiring speaker. Ron Balliser, who is a learning health system oriented chief innovation officer at Clalit in Israel, who helped bring us much of the data and research that led to our understanding of the Pfizer vaccine. That's published in a series of New England Journal papers. Karen Copenhaver, who is an e-commerce lawyer, including for the Linux Corporation, talking to us about the proper use of open source, and Robert Langer, one of the most cited engineers in history. We, like Mihaela, would love to hear from you, and we're also collaborative and always looking to expand our training program with new trainees and grow our faculty. So please do reach out to us as well. And thank you everyone for joining us this afternoon.